up, down, out. So you start over again. So you have it facing towards you. So we're going to address that in just a minute. And that's always, of course, fun. There's all kinds of fun little psychology tricks to do with kids. That's something we're going to touch on that in a minute. Does anybody? How many of you actually know? Have seen this before? How many of you know how it works? Okay, well we'll touch on that. So go ahead and sit down. And then the other question, just to sort of motivate things a little bit, as I was talking with Harold on the way over, and the question came up. So I'm just curious. I'd just like to take a poll. I have one of my favorite mathematical props here. I'll be using shortly, but it raises the question. So as a lettuce leaf grows, and those of you who garden know this because by just observation, if you think about it. But as a lettuce leaf grows, does it become more crinkly, less crinkly, or the same crinkly as it gets bigger? What do you think? Does it go more crinkly, less crinkly, same crinkly? I have no idea. Well, there's actually a very strong mathematical reason for what it does. One of those things, and not only does it do one of those things, there's a very, very strong mathematical reason why that's exactly what it must be. And so that's something else that we're going to talk about. And that's true not just, of course, of lettuce, but sort of universally true for all kinds of crinkly surfaces which abound in the natural world. So today what I'm here to do is to discuss some ideas about curvature of surfaces, which is one of my favorite topics. I'd like to just talk for a moment about some of my own work to introduce myself. I have to say I find that a little bit embarrassing, but Dave asked me to do so. I guess some of its relevance, particularly to, I've been involved with mathematical outreach for essentially my whole career, even before I had a career. So this is what I do. So, does this work? Is this okay?
Yeah.
Okay, so, so one of the things that I've been involved with since I was basically an undergraduate is just making all kinds of cool, sort of fun, just gizmos and particularly handouts and nonsense like this. So here's sort of a sample. I'll show you a few of these in just a second. This is a little comic book. It's called Infinity Number 1. It's not really a comic. What it really is just a bunch of exercises and things of this sort. And this is from about 20 odd years ago. But one of the things that I learned, and I would highly recommend that you think about as you sort of do outreach, is that lots of freebies of various kinds make something, surprisingly wonderful for the kids. And so, just to demonstrate that, so here's so in this Infinity Number 1, it came with a set of stickers. It came with a sheet to cut out and put together, along with all these puzzles and lots of hands-on things. So everything I do, I try to include lots of stuff like that. And so, for example, here's one that I made a few years ago. It's an octahedral pencil holder, which you'll never guess really how it works unless you actually cut it out. But the pencils weave through each other in a surprising way. Or here's some stickers from that Infinity Number 1. So this is about 20 odd years ago. Or here's something that I have for you today. So this pretty much guarantees that you will ignore the rest of my talk, but nonetheless, yeah, go ahead. So just the way these work is that there's not really one of everything for everybody. So you're going to have to kind of investigate. Sorry, I gave you more or less straight up. So you're going to have to kind of investigate and sort of even it out yourselves. And there's plenty more. So if I botch this up, you can oh wait, I'm sorry. No, wait a minute. Here. A lot more. So if I botch this up, you can have it. Now, of course, I do want you to pay attention. Here you go.
Somebody did it to me. I think everybody else did.
So anyway, these are the Ptolemy math cards, and you can have fun looking at those later or now. One of the things, I guess, that really, I suppose this is what Dave wanted me to talk about. So one of the things that I started, it was literally 20 years ago. It was 20 years ago last Wednesday was the first one, March the 6th, 1993. I started the Saturday morning math group at the University of Texas, and it's incredible. It's still going on. And one of the things that, there's sort of a number of things that are relevant, I think, to this group. So essentially, this is like a prototype of maybe sort of a Julia Robinson festival type thing. I attributed some of its longevity really to this idea that, the students come in and they don't just listen to a lecture, but then they have a lot of hands-on activities. There's a lot of freebies. There's a lot of swag that comes along with the Saturday morning math group. There's a number of other things, like one of the, just by accident, when it started, I actually only led it for one semester, and then I turned it over to another graduate student. And that was just because I was about to get my PhD and move on in life and so on. That turned out to be a remarkably wonderful and important thing, because what it meant was that the next somebody else had total ownership over it, and then the next year somebody else had total ownership over it, and so on. So now it's passed on like some cherished thing. But also nobody wants to be the one that kills it. So that turns out, so that's really one of the reasons why it's gone on this time. And I'm not really in touch with them, so I don't really know what its current state is, but they're still attracting students, I guess. It's still going on. I don't think they even really fully knew that it was the 20th anniversary. One of the things that I'd like to sell to you a little bit is the Math Factor podcast, which is something that I've done. It's sort of a little bit on hiatus. But this is a podcast which I had for several years. If you look at the archive, it's just got tons and tons of stuff. I was hoping to maybe play a little bit of it for you, but what's really nice, I guess at its high point, it was pretty popular in its way. I guess a couple of years ago, Vi Hart came and talked to you. So a good yardstick for the Math Factor is it had 1/1000th of the popularity of Vi Hart's videos, which I take as great. That's really quite a high standard, actually. So, no, I had a few thousand people regularly listening to it, and if you do check it out, there's several things about it that I was very pleased with. So one reason why it was so well regarded, I guess, in its way, was that I was doing it with a local radio person present, and we have a very good rapport. And he's not a mathematician. He didn't really have any mathematics after the 10th grade, but he's a remarkable interviewer and able essentially to talk about anything, even if he doesn't. He's just an amazing conversationalist. And so that really comes through. But then also, one of the things that I was really trying to do very, very much in this was to talk to lots of different kinds of people about their mathematical experiences. So there's a lot of book reviews with authors about mathematics. There's a lot of interviews with recreational mathematicians, with kinds of people, plenty of people, familiar names. There's a lot of there's some man on the street, interviews. One of my favorites was we went to the farmer's market and set up a booth and said, ask a math question, and take the results. And most of them were pretty lame, but it was pretty entertaining. The surprising number of people wanted to know, had some mystical question about pi, particularly. But I have to say, I think it is pretty charming, and so that was one.
Could you say again what that website is?
This is mathfactor.uark.edu.
Mathfactor.uark.edu.
We will put slides up on the web.
Mathfactor.u Arkansas. I'm at the University of Arkansas.
Okay.
uark.edu.
And it's linked on the 2013 mathematical.org.
Okay.
All right, and then here's a little CD we made. One of the things that's important to me as a mathematician, as a math expositor, is to put in sort of kind of ridiculous humor. I guess it's my sense of humor. And so, but I think it's also an effective way of disarming people. So if you can find the jokes on the back of the math cards, that's good. But anyway, this is sort of the back of our Math Factor CD. See, it says, I don't know if you can see it, but it says, oops, it says, America's fastest growing math radio sensation, which I guess there's essentially zero competition for that, so. All right, so, and then that's the CD itself. And then I guess another thing that I've been involved, I do is I make a lot of art, which I want to talk about in just a minute, sort of the role that plays in mathematical outreach. But I have a site, mathfun.com, which is just chock full of this kind of nonsense. And I guess I also want to sell that to you. So the thing about this site is if you just hit the random button, that's the best way to appreciate it. So I'm going to put that. So, sorry. Beg your pardon. Anyway, if that had worked, you would have gotten the idea. So, and then I guess another thing is sort of, it's closely related. So kind of this is sort of a sales pitch again, but it is really all tangled up with the idea of making mathematics accessible and engaging and intriguing to people that wouldn't really think of what you're up to as mathematics. So this is a book, The Symmetries of Things, that John Conway and I and Heidi Bergel wrote. And it's full of all kinds of pictures. The basic idea is to talk about symmetry in terms of the topology. It's relating symmetry to topology, so it's full of basically every symmetrical pattern is associated with a particular kind of surface that you get by folding the pattern up. It's not the point of the talk, really, but so it's got all these kinds of pictures and so on, and it gives you ways of approaching other kinds of symmetries. But I guess what I'm really, again, one of the reviews really nailed it in American Scientist, which is that what we were trying to do was to ramp, I mean, it's a serious book, but looking at it at first, you don't really realize it's serious at all, because it ramps up very, very slowly. Ultimately, it gets to sort of a research monograph, right? But you can't really tell because it's filled with all these silly pictures, and the first 100 or so pages is very easy to read for a very broad audience, and it's sort of easing people into the topic. So, think of this. So anyway, Symmetries of Things by Conway, myself, and Heidi Bergel. And then, like everybody here, I've done plenty of outreach stuff. This is a nice little, well, you can't really see that, but that was sort of something I did with some students a few years ago. So this is essentially a random collection of things. One of the things around town that I've done a lot of is sort of participation art, and I want to talk a little bit more about that in just a moment, but getting people to show up and then make something collectively that they really didn't know what it was, or basically giving them as simple as possible directions, and then something interesting comes out of it. So here you can't quite see what that is. Oh, here's some kids. Okay, so this is these are some bamboo stars, and it's kind of a shtick, once you get something like this, you just kind of use it over and over again. But the point is it works. People show up and they make these things, and they know about them, and they know there's sort of a reputation around town that there's going to be one of these star building things that you should, it's worth showing up for. the newspaper photographers know that it's going to be reliably interesting. Yes?
Could you say what the simple directions you gave?
No, because the secret, I can't. I can give you a file. The secret is this thing here.
Ah, I see. So the scaffolding.
The
Why is
secret,
it
right.
scaffolding?
So the scaffolding, I can give you plans for the scaffolding. And then, well, once you have the scaffolding, it's really easy. You just stick the thing together, stick the scaffolding together, you feed the bamboo through, and you remove the scaffolding and let the sauce. No, but that's the secret sauce. And that wasn't so easy to come up with. And so this is a completely different event called Bamboo Palooza. This is a completely different event. This is a group of students making a hyperboloid. And by the way, I guess if you've never seen this, this is a wonderful thing. It's a lot like the finger trapper toy, you know, except it's exactly the same principle. So, of course, a hyperboloid can be made by rotating a line, a skew line around an axis. And if you do that in two directions, then you get a very strong structure. But if the joints can flex, then it's actually flexible. And so what this is a series of, it's like 50 bamboo strands, and then they're tied, but in such a way that they flex. So the thing actually will collapse up and come out and make a little party room, basically. It's actually quite large. And then here's another one. This is an enormous structure. You can't really tell the scale here, but it's about 200 feet from one end to the other. And again, one of the stars. It's I guess the height here is about 20 feet. And this was made in 90 minutes. Literally 90 minutes from sticks, yeah.
Is bamboo native to Arkansas?
But it grows everywhere.
Does it?
Well, yeah. We have a small bamboo that's native. There's one species of North American bamboo we have that.
So where do you get this one?
Oh, it's all over the place. It loves Arkansas. So, and this was done in about 90 minutes by 200 architectures. by about 100 architecture students. It's a very fast system for weaving structures. Oh, there's that again. Okay, this is sort of random. That was pretty fun. Hang on. Somehow this got out. Well, this was. I just wanted to go to this. This was another one of these woven structures that we did. We had a century ice storm which destroyed a lot of trees, but the structure is just fine. But this is the same kind of technique as that woven wall was. So that was.
And what's that constructed from?
What's that?
What's that constructed from?
Both of these are wooden lath. So we live in a wood-producing region, and so there's lots and lots of various kinds of scrap wood. So this is actually milled from. There's a company that makes moldings for, whatever, and so they trim. These are the trimmings from that. So they're very nice because they're 16 feet long. They're a uniform height, but the thickness varies from nothing to about 1 inch. And so it's simply woven. It really is. It's just woven. In fact, there's no nails, there's nothing besides the tension of the wood itself that's holding this thing up, which is pretty cool. Okay, and then I guess this is all some various events, again, I really like making these kinds of posters. That was fun. Again, like this kind of hyperbola, it just sort of, you better be astounded, damn it. It's sort of part of the humor of the thing, just to be. And then this is, I guess the reason I'm bringing this up is that this is very much like the Julia Robinson Festival that we did yesterday, and so I'm trying to get something started like that, and so I found that very interesting. This sort of nuts and bolts talking shop was useful. Seeing something like this. In fact, just for example, even that there was a photo release. When we came in, we had to sign the photo release. I was like, right. So here's our our Celebration of Mind festival, and we got the entire department involved. And I guess And then, okay, so then this is another thing. This is last summer. Harold took this photo, and I guess this I really like. So I've also been working with little kids with Harold right there at Epsilon. Okay, so I guess the final thing I want to talk about is one of the, I guess the general aesthetic that I'm trying to bring to all of these endeavors is one where it's essentially trying to create a sense of massive collaboration to do something. Now, I mean, it may be really designed, like the next things I'm going to show you, I mean, it's sort of collaboration in the sense that people are showing up and they're making something, but on the other hand, they were just told what to do. So, but it goes from that all the way towards, I think one of the things I'm doing now is I'm chair of my department. And I view that in exactly the same way. I really fundamentally view being chair as another kind of art form where the medium is all these people and I'm trying to get them to do things like create a math festival, right? Or to change the way we're teaching, or to have a different attitude towards mathematics than, you know, all of us have experience with math departments. And we all know that some math departments are just really hip, wonderful places to be. And we also probably, most of us know that many math departments are just kind of these hidebound, dead-seeming, you know, everybody grinding along and not really actually able to enjoy and communicate the beauty of mathematics, right? So moving the culture of my department is just another one of these collaborative art projects. And it works. Thinking of it that way really does work. So here's a few pieces, and this is sort of a segue into today's workshop. So here's, this here was one we did in 2008 with a collaborator, Eugene Sargent, and myself. And people, again, they show up, and they have all these coils of metal, and after a little while, it took 45 minutes. They put this together. And what's really neat about it is, as you can tell, it just changes really radically from different perspectives. This is because it's got one of the there's 230 space symmetry groups, 35 of which are kind of interesting in that they don't have a preferred axis. And in that family of 35, there are 8 very closely related symmetries that just are weird because they're so sparse, you don't really understand them. And so this is sort of one of those in that symmetry group. And again, just like if you think about these systems, you could design something where people can just show up and they put this stuff together. Or here's another one that we did 2 years later. What's that? 2 years later at the same festival, the Gathering for Gardner, same collaborator and myself. And our working method was basically I sent him a string of 512 digits that represented which way these turned. So 0, 1, 2, 3, right? And then he made all these. And this was a puzzle. And unfortunately, we left the key to the puzzle in the hotel room, so it was a good puzzle for us as well. And we made this. So that's actually John Conway's son and another kid. I don't know who that is. And that's what it made.
Cool.
So it's sort of like a Hilbert curve, but kind of random Hilbert curve. And then this is, many of you have done this kind of thing. This is playing with zone tools and making this. For a while we had the largest zone tool structure, I think, in the world. Certainly the largest one of this particular kind. And then there's Paul Hildebrandt, the inventor, or the president of the Zone Tool Company, messing around. And then the last one that I have here is, this is the one we did last spring, about a year ago. And people, again, you see these people, they just show up, they make this stuff, and it kind of assembles itself, and there we have the result. So this is very closely related to today's talk. Here we're trying to control the curvature of the surface very precisely. And if you think about it, I mean, this is sort of the very first question of the talk is, okay, look, can you make a flat piece of paper, say, or a flat piece of steel conform to some sort of surface like this, where it's very saddle? And if you try it, of course, it works perfectly well. No, if you try it, the thing is going to have to tear in order to be able to conform to a saddle, that there's not enough paper. And that's actually a real problem when you're making anything out of steel. Like any kind of steel object, if it's really a substantial amount of steel, you either have to use a tremendous amount of force to distort it and change its geometry, or you have to do something where you're stitching it together in various kinds of pieces. So like, for example, ships, I don't really know how they make ships, to be honest, because you can't stamp out a massive piece of ship, right? You somehow have to stitch it together out of essentially flat pieces of steel that you can roll and coil, but you can't stretch. So we'll talk more about that. And that's the piece. And this, by the way, if any of you know, this is a minimal surface, and it's the gyroid minimal surface, and it has the same symmetry as the other sculptures.
How did you get the pieces?
The original pieces.
Pieces that you made?
That's a whole talk. I mean, these are all basically what this is. So this is a part of this is an infinite surface that's periodic, and we clipped out a little piece of it. And then there's and then with a lot of work, I found some nice subdivision of that into some regular chunks. But then they're clipped by the sphere in various kinds of ways. And then we had to figure out how to make them.
Tell me more fundamentally, what is it made out of, and how did you get those pieces?
Okay, go
Oh,
back,
you
go
just buy
back.
these online. No. No, of course not. This is made out of steel that's cut into strips and then molded
Who
onto
did
it.
that?
So my friend Eugene Sargent, yeah. So my collaborator.
Did you need a lab? Is it just
So this was
simple
done by, this is all handmade. It's completely handmade. I mean, the cutting was done with a plasma torch
Can you just go back to the slides that had the individual pieces? There was you had a picture of it, right. So what kind of curvature are those already assembled from?
These pieces this is what we brought to the party. And these are all identical, except that they're clipped by there's this clipping sphere that clips them in different kinds of ways.
Yeah, but it looks like each of those are made from individual pieces already, right?
Yeah,
But,
I guess I wasn't really, I can pull up a different clock if you want. I can
No.
have pictures of this. I can show you during the break if you
Okay.
like. But that's right. They're all exactly the same, so we just figured out how to do it once, and with a lot of effort, actually it's beautiful. With a lot of effort we came up with this, this particular shape that could be then tiled to make this surface. And then that was all done on the computer, and then my friend made a clay model of that, and then a fiberglass model of that, and then we worked out what these curves should be, and they were kind of eyeballed. And then from that worked out a method of taking steel strips and what the shape of the steel strip should be and bending those. I mean, it was months of work. And then he cranked out, there's hundreds of these strips. I mean, labor is the biggest part of this.
sure. Yeah. Thank you.
In any case, what I'm going to talk about today is curvature. This is the last thing. This is very closely related to what I want to talk about. It's sort of an advertisement for MoMath, the Museum of Mathematics in New York, which is a fantastic museum which just opened last December. And I helped with one of the exhibits, which is closely related to today's workshop. And so the Shape of Space exhibit. So the last thing is, this is in my front yard, and this is what we're going to do. So how do you make something like this? What is this thing, and how do we describe what's going on here? So here, if you look at it, it's made of pentagons and squares, but what's really weird is that these are not 90-degree angles. These are like 86-degree angles. This is 116 degrees or so. So I guess we have some breakfast waiting for us.
Yes, room 315.
We'll reconvene in the next room. Oh, thanks.